Okay, Math 170. For section 1.7, I've been very excited to share with you. Finally, we get to talk about the precise definition of a limit. I hope you are excited too, as I am. When you're going through these, I just want you to be real patient in trying to understand the concept behind this. These took about 300 years to develop. And Newton never fully understood this, and he's the one that invented calculus. So hopefully, you just gotta give yourself a little bit of time here. It's okay if you take more than 5 minutes. We just hope it doesn't take you over 300 years to figure this one out. So I want to get started with the notation that we use when we talk about epsilon and delta. I decided to write it out in English so you would see, but it's very nice to look at epsilon. It's the lowercase Greek letter. And then we also talk about delta. It's kind of like a D with a tail. And I'll read it out and we're going to make sense of it as we go. But we want to let f be a function defined on some open interval that's going to contain the number a. And maybe it doesn't have to contain the number a itself. So let me see if I can draw something on that matter. So maybe it doesn't really matter what's going on, but let's go something like this. So it doesn't really matter what the function is as long as we have an idea. There's our function. And we want to talk about that we're containing a. So we're going to look at, I'll mark where I want the a to be. Anywhere on the x-axis. And what we're interested in is we're looking again, revisiting this from section 1.5, we're looking at the statement, limit of f of x as x approaches a equals L. This is going to mean for any given epsilon greater than 0, so let me see if I can try to demonstrate this. So I'll go with finding the value on the function, finding the limit, there's my L, and we want to talk about the small distances from the limit. So remember in section 1.5, we were trying to talk about if we want to be within 1/100th of a unit from the limit, or 0.2 within the limit of within the distance of the limit. So we're going to talk about this distance. We're going to call this epsilon. So if I can, see if I can write this out. I've got maybe a little portion here where the distance, and I'll highlight this in pink. This distance right here is considered epsilon. And if we were going to notate this on the y-axis, that would be the limit plus whatever that epsilon is, L plus E. And similarly, if we want the same distance below the limit, so 2 uniform distance, and there's where our epsilons are coming back in. We're going to denote this as L subtract off epsilon. So what we were looking at in section 1.5 is we were trying to see if we set this value of epsilon, we're going to go to our function on each of these, map it back down to the x-axis. I want to draw a little bit straighter of a line, and it's useful when you're going through this. Take a little time on this to draw this out. It makes the concept a bit more clearer rather than just watching. So do a few of these on your own. But we talked about the corresponding x value. If we knew this particular y value, we looked at this as, we noted it as x sub 2. And also, if we looked at the corresponding x value as we map the L minus E down to the function, we called that x sub 1. So what we're interested in when we were going through section 1.5, we were interested in the distances from A. We wanted to figure out what's the distance from x1 to A and the distance from x2 to A. And those distances, and I'll write them out in, it's nice to see in the absolute value mode. Those particular distances, so the distance from x1 to A and the distance from x2 to A, those are dependent on where we draw the epsilon. So we select this value first. And just so that we're clear one more time, it might be a little hard to see because we have a little bit smaller, so maybe I can zoom in just a little bit. The distance from L to L plus E is considered epsilon. And again, we have the other distance from L to L minus epsilon. I call it E sometimes. Well, we all kind of do sometimes. So those are the two values. Notice they're the same distance from the limit each time on the y-axis, but when you map them back down to the x-axis, you may get two different values of where we see this. So if I'm going back to the limit definition, we're looking for this distance. And when we did section 1.5, we didn't really define this yet, but we are actually going to refer to these distances on the x-axis as delta. And it happens to be the smaller of the two distances that we just described. I always talk about the yellow highlight or the teal highlight, but we're looking at either x1 minus A and x sub 2 minus A. And just to kind of map this back so you see this, I highlighted yellow, that's the distance between x1 and A, and teal, the distance between x2 and A. And if we look at our graph and we inspect it, it does appear the way we've drawn our picture, according to our graph, it does appear that this is smaller. And if we stay within this distance, I can see if I can highlight this along the way. As long as we choose the smaller distance, it's about that long, we are guaranteed to be within the limit. So it's very, very profound. So let me write this down for you so that you have that. It's really nice to have formal notes, so take your time. So if we stay in this distance, we are guaranteed to be within the limit. So if I can kind of make sure we're going through this, just to restate this delta that we are finding, we're trying to emphasize that no matter what we choose epsilon to be, we should be able to find a delta that satisfies this definition. And so this is what all this notation over here is talking about. The delta has to be a distance greater than 0. And then of course, when we choose the within the limit, we're going to stay within the pink part, the f of x minus L, the distance between the function and its limit. So I'll erase that because I don't want to make things too messy. We are going to try this with a concrete example. And by the way, I'd like to point out, we do have some Desmos graphs that would help you explore this. Sometimes if you want to try a bunch of different values and look for your possible visualizations of your delta, these epsilon, delta epsilon, excuse me, the Desmos graphs definitely help us see this a little bit better. So I'll bring that up after we go through this. So a little concrete example. It's one of our first experiences with proofs. And usually what I do when I'm proving these delta epsilon pieces is I like to write out the actual definition so that you can kind of break this up into, it's about 3 different parts. Let me see if I can write it out in general. So I'm going to recopy what the definition is. So for any epsilon greater than 0, there is a number delta greater than 0 such that 0 is less than x minus a, that's the distance, is less than delta. So delta is looking at this distance between the x1s and the a's, x1 and a, x2 and a. So if that is the case, if all this happens, then, and I'll use a little bit to the right, f of x minus L should be within your limit. So the distance between your function and your limit should fall within the distance of epsilon. So this is a 2-step process. A lot of times what we like to do is we like to write out our thoughts so we can work this through, and then we have an actual proof that we're going through. So just kind of make sure when we talk about our thoughts, it's kind of like our scratch work for our actual formal proof, rough draft. So we have thoughts, and then we have the actual proof. And if I were to collect these, you're going to want to clearly label this because you're going to need the proof for credit. So don't forget, clearly label this as the proof so I don't get confused between your scratch work and your thoughts. So what we want to try at this point, I'll look at this way. Now for any epsilon greater than 0, so we're going to start off with the hypothesis of this statement. Okay, so there's a few parts going on. For any epsilon greater than 0, there's the number delta greater than 0 such that this is happening. And if that is the case, then we could talk about the conclusion. F of x minus L, the absolute value of that, or the distance between the function and the limit, is less than this value epsilon. So I'll rewrite this one more time just to make sure. The more we rewrite it, the more we have it in our minds. So the thoughts. So I'm clearly labeling my scratch work. For any epsilon greater than 0, we want a number delta greater than 0 such that if, let me write this down a little bit better, the 0 less than distance between the x's and the a's, x1 or x2, is less than delta. If this is the case, then we'll spread this out because I'm going to start filling in some pieces to our part. So I'm going to write kind of how this applies to our example. So if this is the case, then f of x minus L, absolute value, should be less than epsilon. And so one more time, just so that you're seeing this, we have ourselves the hypothesis right here. Everything we assume to be true or we're trying to make set up, so that if everything there is true, we're going to talk about our conclusion of what we want to show. And I may need more paper than I originally left here, so keep that in mind. So if I'm going to my definition, I'm going to go back to my limit notation right here. We're going to maybe kind of start labeling who's our A, who's our f of x, and who's our L. So just kind of remember the way we set these up. According to how we write limits, it looks like we're going to see that the f of x, see if I can color code it a little bit more. I'll do this in green for now. So we have our f of x is 2x minus 1. So sometimes if I'm going through my proof or my definition, I may kind of label these parts right in here. I have 2x minus 1 being represented as f of x. My x value that I'm trying to approach, if I can find that, here it is. Might be hard to see, it's a little small, but x is approaching 3. So we call the A is 3 according to our proof. So I'll put that in there a little bit above here. And then the actual value of this expression with the limit is actually equal to 5. So I'll also put that in there as well. It's going to be L equals 5. And that should be right about here. So all I'm trying to do is fill in who is A, who is f of x, who is L. And then we'll deal with the epsilon delta part from here. So the idea behind all of this, once we figure out where the notations are, we're going to want to take this last part out. And I like to think about it as another strategy is I work backwards and then go from here. We're going to figure out how to take this part, starting off with the function, a little more complicated side. We're going to manipulate this algebraically until we can pull out according to what we want, an x minus 3 somewhere. And where did I get that x minus 3? Comes from the original setup. The x was approaching 3, so that's why I was filling in for our particular value there. So let me undo that. I don't want to write too much in there. And what's going to happen is no matter what we do, epsilon is always a function of delta. So it's going to be useful when we're going through this. So if I'm starting off, the idea, we are working backwards, and this is why the thoughts part is useful. Sometimes you can't tell going forward what to look for. So this is why it's another proof strategy. So let's start this off, and maybe I'll leave myself I'll have to leave myself a lot of room. So we're going to have to use the side. So I'll start off over here to the right. Lucky me. Okay, so we're going to talk about, again, we're still on our thoughts part. And I'm going to talk about the starting point of my thoughts. So the idea was to take the part that we were trying to show, the f of x minus L. So that's 2x minus 1 minus 5. And we're already trying to show that it's less than epsilon. So we're going to assume that that is the case. So a lot of times what happens when you go through this is you kind of play with a lot of the math that you already know, or what would lead you to maybe simplifying what's inside this absolute value. So sometimes you can say, okay, 2x minus 1, subtract off 5. We don't really need the parentheses. This is going to turn into 2x minus 6. Okay, and we're just assuming that we're still less than epsilon. We haven't done anything with the inequality symbol. So remember what our goal was. Remember our goal was to try to figure out how we can pull out or look for a way to get x minus 3. And so a lot of times when you're looking within your absolute value, factoring tends to be the next role. So if we can do that, I can take the 2. I factor that out. That in fact becomes 2 times the quantity of x minus 3. And so we're still in the absolute value. So this is looking promising. This is exactly what we're looking for. It's going to help us with the rest of the idea. So now we're going to use some values of absolute, or some properties of absolute value that you probably haven't done in a while, but it does end up making sense. So these statements that I'm showing are equivalent. What happens when you have a product on the inside of an absolute value? According to this property, maybe I'll write it off to the side. Little absolute value property. And remember what we said about pulling things from your past? This is exactly an application of this. So if you have 2 absolute values being multiplied, we learned that we can say, oh, that's not a big deal. We can combine them on the inside of the absolute value. But the way I'm seeing it, I did exaggerate that multiplication symbol a little bit too much, I think. There we go. What we're looking at is we're coming from the right to the left. So we see ourselves having a product. So if I were to break this up, this is now going to become the absolute value of 2 multiplied by the absolute value of x minus 3. Equivalent statement. And we are still less than epsilon. And this is promising because when we actually have the absolute value of x minus 3, if I can kind of pull back to what we were trying to show, that's about right here, this part. We're actually looking at on our way, or we are on our way to figuring out who delta will be. If we can get the x minus 3 part isolated, which by the way, what's the absolute value of 2 is just a 2. We don't have to worry about the bars anymore. We have 2 times the absolute value of x minus 3 is less than epsilon. If you're going to solve or isolate the absolute value of x minus 3, we are dividing both sides by 2. We're able to do that. 2 is a very nice integer. So we are actually getting the absolute value of x minus 3 is less than epsilon over 2. And that, my friends, is our delta. So that's what we're looking for. So here we found it. So once you find this value of delta, you basically rewrite the process from the bottom up. And this is going to help us with we have to provide logical arguments to get from one step to the other. So the reason why we're doing it this way is we would not know right off the bat what the delta would be. It's really hard to tell by looking at the function. So we have a generic process of working backwards to figure out, well, if we knew this, we can find delta. So just remember, once we find it, we're in good shape. Now, I'll just do this for the sake of notes. We write the process from the bottom up. Providing your logical argument. And I'm emphasizing logical here, so that you can write the proof. Remember, this is probably one of your first times dealing with formal proofs, so this takes a little practice. We like to do a lot of these, and then you start to get the hang of it. But if we're going to go to our formal proof, you're going to have to see me go back and forth to refer to this. I'm going to label, this is my proof. This is the part that I want to be graded. We are going to start with our definition again. We're going to start with the hypothesis. So remember, we're going to look at for any epsilon greater than 0. Now remember, it says we want a number delta greater than 0, but we found it. So we're going to state this. Let delta equal, and this is the value we found when we were working backwards. So I go back and it was epsilon over 2. So I'll kind of circle it to remember. We found this. Now, we're going to try to take the first part of our hypothesis, or I guess it would be the last part of our hypothesis. This is the part of where we're seeing the absolute value of x minus 3. So we're going to assume this is true. That's usually what happens in proofs. So now if 0 is less than the absolute value of x minus 3, and we already know it's less than delta, what that means, we already know the value of delta. We can always assume that the absolute value, since it's already a distance, it's going to be positive. So we can be a little, less formal, and we can drop the 0 at this stage. Absolute value of x minus 3, what was our delta that we found? It was the epsilon over 2. So I'm going to write that in red just to remind us. And now we're trying to figure out how we can get the concluding statement. How are we going to start from x minus 3, absolute value of x minus 3, to get the concluding statement? And so this is the reason why we went backwards. So right now, I'll shrink it so we can see this side by side. Well, we'll have to look. Right now, we are at the very last part of our thoughts. So if you are able to show your forward process with your thoughts, working downwards, now the job is to just take all of the steps that you wrote, and for the most part, you can write them in reverse to get to the concluding statement. So this is where we're saying, okay, well, how do we get epsilon by itself again? We're kind of saying, okay, that's the second to the last step. If I can, I'm going to open this up just a little bit more, just so that we can see our thoughts. You can multiply by 2 on both sides. So that's going to leave us with 2. And I'm using my implied statements. 2 times the absolute value of x minus 3 is less than epsilon. So that part's kind of, you can kind of tell what that works as well. But a lot of us wouldn't be able to tell ourselves to add in the absolute value bars around the 2. So what I'm looking at is the next step, I'm just working in reverse, just justifying why I'm able to do stuff with properties. That's a proof. Let me write the 2 in blue. So it's true. When you see a 2, it's also the same thing as the absolute value of 2. Let me write that epsilon a little nicer. And then now we're using the absolute value property in reverse. we're saying, okay, well, that's the same thing as taking the 2 and distributing it in. Still less than epsilon. And then now it's a little bit of an algebra matter, 2x minus 6. That part's nice. Now here's where we have to get a little creative. And that's the reason why we worked backwards. You know, how would you know to break up the 6 with the 1 and the 5, or whatever numbers were in your proof already? So this is where we're saying, okay, let's finally look at our original step that we had in our thoughts. And we are taking, instead of writing 2x minus 6, we're breaking up the 6 as negative 1 minus 5. So we end up having 2x minus 1, subtracting off of 5. So when, oh, make sure, don't forget that you're writing the less than epsilon part. Once you reach that part, by the definition of what a limit is, you figured out who the f of x was, you got the limit. And now that you have that portion, you actually now can say, finally concluding, therefore, the limit as x approaches 3 of 2x minus 1 is equal to 5. That is the definition of the limit. Whew, that's a tough one. So let me kind of shrink it down a little bit so you can kind of see the side by side. And just re-emphasize, let's kind of rehash this. Whenever we're doing these delta epsilon proofs, the idea is on the side, we like to start with what we were trying to show. So this is where you start filling in who's the f of x and who's the limit, who's f of x and who's L. Then we use algebra to see what we can do to figure out a way to see the absolute value of x minus a in the proof somewhere. So we kind of play with a lot of factoring stuff out, a little bit of absolute value properties. And once you can get the absolute value of the x minus a, you just isolate that, and that allows you to find your delta. So that's what we were looking for right there. When you find your delta, you start the proof with the formal definition or the formal hypothesis. You start off with what they assume to be true. Epsilons are greater than 0, it's a distance. And then you state who the delta is. So check, got that. Then you start off with the last part, the if part. So you assume that that's true, but you fill in your particular delta. Then we work our thought process in reverse so that we could eventually get down to showing the conclusion or what we were trying to prove. And once we have that, you automatically go to the limit notation. So you can rewrite it because that is the precise limit definition. Exciting, huh? So let's visualize this one more time. Sometimes when we see the proof, it doesn't really make sense to us. So let me see if I can draw it out with a graph. Maybe we can bring up the decimals to help us out a little bit. So I kind of blew this up just to make sure. So let's kind of go back and rehash. We had the statement or the proof. We had the limit as x approaches 3 of 2x minus 1 equals 5. And if we're going to draw this out, a lot of times I'll just draw an XY axis. And I'll exaggerate it a little bit just because we want to see the distances. And so I always have to go back to notating like who is my function. And according to the notation, my function is 2x minus 1. So that's a line with y-intercept -1. and slope 2. So we go up 2 over 1, up 2 over 1, and we can be accurate if we need to. You don't always have a ruler. I'm working on my straight edge here. So we're going to do our best to be accurate about these. Sometimes it doesn't. Yeah, it brings everything up. I'm trying to use a straight edge so that I can make this pretty for everyone. Oh, it works out, okay. Okay, now, what we're assuming is we kind of already are looking for the limit. So the limit is at 5. So the y-axis, 1, 2, 3, 4, 5. And they're asking what's happening as x approaches 3. So I go on the x-axis, I'll mark where the 3 is, and I'll kind of map it to where I see my function. So I have x equals 3, it maps to the y-axis where the limit actually is. Now here's where the epsilon delta comes in. The first thing we're looking at is we are trying to talk about letting epsilon be a certain distance away from the limit on the y-axis. So let our epsilon, in our case, let's make it 0.1. It's always a very small distance. You get too large, you get too much of a delta. So if this is the case, you can kind of play around with what we're going at. We can look at where the limit is. We talk about 5 plus 0.1, and here I'm going to exaggerate, even though it's not quite to scale. That's going to give us 5.1 on the higher end of the limit, or the y-axis, I should say. And on the lower end, same distance away, that's going to give us 4.9. 5 plus 0.1, 5 minus 0.1. So again, we have the same exact distance. Let me mark this a little bit. We have epsilon distance from 5 to 5.1, the same epsilon distance from 5 and 4.9. Now, if you already know who epsilon is, we've already calculated the corresponding delta to reach everything within our limit. So if epsilon is equal to 0.1, I think I put a greater than symbol. Hold on, let's do this a little better. So if this is the case, then our delta, remember we found it was epsilon divided by 2. And epsilon divided by 2, in our case, we found 0.1 divided by 2, and we do a minor calculation to get 0.05. So if we want to play around with what should work out, we can go forwards and backwards. But remember, when we talk about mapping everyone back and finding the upper bound of your x's, we map it back down to our x-axis, and that gives us our x2, just because it comes a little after. And then same story, we do the same thing with the 4.9. We map it to our function, map it back down to the x-axis. That's going to give us our x1. And what we are concerned about is relying on our distances. So remember, we have the distance from x1 to 3 and the distance from x2 to 3. And in our case, what we're looking at and what we proved is that those distances, if I can kind of point to them, I'll write it in blue, those particular distances are our deltas. And in both cases, it's linear. In our case, it's 0.05. Same story. So we have delta distance, just so that you guys are seeing that. Now, if you already know what that is, you could figure out the x2 and the x1 value without having to go backwards. We can either go either way though. If we do that, we can say, okay, well, if we know that the distance between 3 and x2 is 0.05, then we just add. That gives us our x2 equals 3.05. And then if we go backwards, we're subtracting off 0.05. That gives us our x1 equals 2.95. So if we keep x within 0.05 units, we say 5/100ths of a unit from 3, then our f of x will not be more than 0.1 units away from our limit 5. So we're kind of rehashing what we did in section 1.5. So if you're kind of having a little bit of trouble with 1.7, do a lot of 1.5 examples so you can actually see concrete numbers. And then it kind of helps with the understanding of what we're really trying to do in this section. Feel free. We can go to Desmos. I can kind of show you a few things just so that you can play around. These might not be the best interactions, but it does help out. So let me see if I can pull that up for you all. I'll leave this in the link if I can. I'll copy it and paste it so that when you see it on your page, it kind of gives you an idea of what you can type in. Sometimes you can interact with these, and instead of using the function that they gave you, you can kind of see what would work. Sometimes they're allowed to interact a little nicer than others. So some of the Desmos you have to kind of be careful about. I'll try to link you to the right ones. So I have 2x minus 1. Sometimes it takes a little longer to type this in on the screen. So there I have my graph, I think. Press enter. There we go. And what we can do, you can kind of already have an idea of what the limit's supposed to be. So in our case, it was supposed to be 5. Back to the function again, give me a second. Nope, sometimes it's a little harder. See if I can type in on it. There you go, open it up. And so we want to say, where do we want to evaluate the limit? Well, we kind of already have a value at x equals 3. So I can slide it to figure out where I'm looking for. But I'm looking at 3. And you can actually type it in once, I think if you have a computer screen, it's a little easier. I'm on a tablet, so it's a little rougher. There we go. So we could kind of see these bounds within the function. Now, if you're interested, I know there's a lot of complication here. You could actually set the value for epsilon. So we were kind of looking at, we had epsilon equal to 0.1. So you can slide it to kind of see the relationship, if this helps you. You can also type it in to make it a little faster. So we have our epsilon being 0.1. And then you could kind of see if you wanted to play with your delta to see what would work and how this is applying. Makes it a little prettier of a graph. We figured out our delta was, remind me, it was 0.05. So somewhere over there. So it's giving you the bounds around 3. That's going to guarantee you to be within that blue distance within the limit. And with these, a lot of times, play around with it, but you could kind of press play and you could kind of see what happens to epsilon, what happens to delta. Sometimes it's helpful to play them at the same time, and you can kind of see how it stretches out. So I really like these because it makes it come alive for me. So feel free to play around with that. There's also another one. It's called the epsilon delta game. And it's kind of the same idea, but I would not change the function because I think it's they're really interested in just using x square. But you can kind of set where you want your limit to be, and you could set your epsilon. So let's say we wanted our epsilon to be 0.5. I'll make it 0.5 just to make it. I'm sliding it, so I got to be a little more there. There we go. And let's say we knew our limit. We wanted it to be at 4. Then you could kind of slide your delta back and forth. And when you make this guy smile, it means you're within the right bounds. Right there, so you can kind of play with that. I thought that was really cool. So feel free, play around with that. There are animations. If you push play, you'll kind of see what works. But sometimes it's so subtle, depending on how large your epsilon is or how small your delta is, you don't see him smile. So I'll leave that up for you. So back to a few more proofs, just to kind of get you used to this. Kind of a big part of mathematics. We're going to do a similar problem, a little bit more complicated. To get you the hang, get the hang of it. So let me go back to my screen. There we go. Sometimes I write a little larger on the tablet than I do in my regular writing, but let me see if I can make it like I would do on paper normally. So they want us to prove the limit as x approaches 3 of the function 2/3 x plus 2 is 4. Again, using the epsilon delta definition of a limit. So a lot of times, remember, I like to write it out to remind myself what are the first few parts. The proof is going to be clear. So this is just the definition. For any epsilon greater than 0, let's make that epsilon a little bit nicer. So for any epsilon greater than 0, there is a number delta. Such that if the distance between the given x value and your bounds is less than delta. So I should say delta is giving you the distance between your x1 and a and your x2 and a if we're speaking more in pictures. So if this is the case, then we can say we are within epsilon units away from the limit L. So just remember, we're looking at the hypothesis, which is the first part, and the conclusion. That's kind of what we're going to want to show. And it's helpful when you start to start filling in who the f of x, who the L is, and who the a is, just so that you kind of know what you're looking to prove. So I'll do that. So if I can look at my particular part, I'm seeing my f of x is actually defined. This part is 2/3 x plus 2. My L, my limit should be 4. My A should be what x is approaching. So in this case, it's a 3. So this kind of gives me a better idea of how I'm starting. And if you'd like, you could draw maybe a vertical line down your paper, and I'm gonna leave more room for my proof. But sometimes the thoughts take a little longer. But I have my proof on the left, and my thoughts or my scratch paper on the right. And sometimes we refer to scratch paper as something that we would throw away, but this is pretty valuable, so I would recommend writing this out organized. Now, we can go with our proof. We always have to start off with for any epsilon greater than 0. So let's go with the thoughts before we write our proof. For any epsilon greater than 0, we want a number delta greater than 0 such that if 0 is less than, remember we have the x minus a part, so let's fill this in. X minus not a, but we want 3. We're trying to approach 3. So if this is less than delta, then at the end, we're going to want the function, that's f of x minus L, so that's the 2/3 x plus 2. So that part, we're subtracting off who the limit was, which is 4. We're looking to figure out how that can be less than epsilon. So when I'm kind of going through this statement, when I start with what I'm trying to prove, I have to think about, we're going to need to figure out how we can manipulate this algebraically so we can get an x minus 3 absolute value of it somewhere. So that's our main goal when we're working backwards. So if we kind of play with this statement, I'm looking at trying to say, okay, usually when I see parentheses, it might be useful to just combine like terms. So that's kind of nice. So we have 2 minus 4, we have a minus 2. Still less than epsilon. I'm going to keep that in there so I don't get confused. But it's kind of not obvious to me. Like the previous example was quick. I can factor out whatever the 2 was. I already got an x minus 3. So I'm going to go with the same idea. I'm going to try to factor. I want to get a single x. So might as well see what we can do if we want to factor a 2/3 out. But you'd have to do a little thinking, because if you factor a 2/3 out, you have to say, okay, if we're going to do this, it would be 2/3 times x. And the question is, we don't know what we're going to get. It's not as what's the word for that? Straightforward? Yeah, we'll say that. So we just have to figure out if we're going to double check. Just a little another thought process on the side. If I'm trying to get a 2, I'm trying to say, oh, someone's trying to participate too. She's just as excited about these delta epsilon proofs as I am. So we've got 2/3 times what is going to give me 2. So you could kind of test things out, but I mean, some of us see these faster than others, but the way I see it is I'm seeing 2/3 times 3 equals 2. So when I do the factoring, I have my next step finally. It takes a little bit of time and patience. I factor the 2/3 out. I was hoping I was going to get an x minus 3, but I was not sure. You have to prove it. You have to make sure that it works. What happens if you make a mistake? You have to justify it. So we have this factored out. We're less than epsilon. And then if we're at this stage, we know based on our absolute value properties that we can break up a constant that's being multiplied to an expression. Same thing as the product, which then allows us technically, this is why we're able to take the 2/3 out of the absolute value in the first place. Absolute value of 2/3 is 2/3. So we end up getting 2/3 times x minus 3 with the absolute values less than epsilon. And then it kind of falls into place. We now know that we can isolate this x minus 3 distance, or absolute value of x minus 3, if you were to multiply both sides by 3/2. I know we're in calculus, but a lot of times I still show my steps. I don't want to make little mistakes and ruin it. So I'm actually getting that the absolute value of x minus 3, I'm actually getting that I should have a 3/2 times epsilon. And that, I'm so excited I found my delta. Yay, we got it. Now, once you have it, then you're kind of all set for your proof. We just have to start there and work backwards. So we shall do that. So that's why I kind of have my proof on the left-hand side. And remember, whenever you're starting out with the proof, you're starting out with your hypothesis. So the first thing we can state is it's assumed for any epsilon greater than 0, there is a number delta. Now we already know what delta was going to be. We let delta equal, remind me again, I'll go back down, it was 3/2 times epsilon. So see how, if you're looking at your statement, you're starting with the hypothesis. For any epsilon greater than 0, check. There is a number delta. We had to find it, check. Now, this is what we're trying to kind of manipulate. Again, sometimes we end up getting to the wrong slide. There we go. So we're going to finish off with looking at this piece. That's the last part of the hypothesis that we have to work on. So now, if we have 0 is less than x minus 3, remember not the a, if we have that's less than delta, we're allowed to say, if we know who delta is, this is the same thing as saying absolute value of x minus 3 is less than 3/2 epsilon. Now from there, you could kind of play around with, we're kind of getting the epsilon isolated again. So we're kind of taking this 2/3. We multiply both sides by 2/3. This is where it's coming back in reverse. So you can kind of use the algebra to help you justify, but these backward steps are very useful. Don't always have to think as hard. So if this is the case, see if I can give you the implied symbol. We end up getting 2/3 times the absolute value of x minus 3 is less than epsilon. And then now we know the way it works is we have positive absolute value of 2/3, or we can rewrite it so that we have the two absolute values still less than epsilon. And again, remember it's a product. And that allows us to bring the 2/3 back in. So I mean, pretty much you don't have to justify it, but I'm just re-explaining just so that we catch it. Sometimes we don't see it the first, second, third time. We do it the fourth time, or maybe even more. So we should have, if I'm trying to expand this back in, I have the 2/3 times the x minus 3 is less than epsilon. I'm just working in reverse. You kind of see where we're coming from. Distributing it back in, this is where we're actually going to see part of our function. So this is going to give me 2/3 x minus 2 is less than epsilon. Let's make the less than symbol. Okay. Now we need to figure out how are we going to get that 4 back in. And this is the reason why we went backwards. We wouldn't always know how to break it up. So if we go backwards, we realize that instead of writing -2, we should have rewritten, or we will want to rewrite it as 2/3 x plus 2 subtract off 4. That is going to give us back our original function, and we'll also see our limit. So once you have that statement, you have concluded, you've shown the conclusion. And once you show that conclusion, you are now allowed to finally finish off the proof by restating or stating that you have just shown the limit as x approaches 3 of 2/3 x plus 2 is equal to 4. And that is the end of your proof. I'll pause. It's significant. So we're manipulating some algebra. I'll give you one to play with. We'll do a couple more. Sometimes it doesn't hurt to see a lot more examples of these just so that you can get the hang of it. We'll go with one more linear function. And sometimes I like to kind of point out some of the hurdles we kind of come across. There's not everything is so straightforward. So here's an example of what could happen. Okay, so we're trying to prove that the limit as x approaches 2 of 5 minus 4x is equal to 3, again, using the epsilon definition of a limit. So we can go with our proof and our thoughts. And when I'm first starting, you kind of see me write out my definition. I like to refer back to it so I know which pieces to approach. So for any epsilon greater than 0, there is a number delta greater than 0 such that if 0 is less than absolute value of a, x minus a less than delta, if that is the case, then f of x minus L is less than epsilon. So I kind of always write that out, so I kind of have a guideline of how I'm supposed to start and so on. I write my proof on the left-hand side, my thoughts on the right-hand side, or however you'd like. Remember, you're labeling them clearly. And so as we're going through this, I'm looking at trying to start off with the if part. We're already assuming for any epsilon greater than 0. So let's kind of play with the if part right now. Okay, so if 0 is less than x minus a is less than delta. I spoke generically, but I should kind of fill in everyone as I go. According to my proof, or what I'm supposed to prove, it looks like the a should be a 3. Let's see what we can do there. Oh, why did I say 3? So used to the other 2 examples. Scratch that, it should be a 2. So let's go there. So if it's supposed to be a 2, what we're really looking at is we're starting off at absolute value of x minus 2. Should be less than delta. We don't know what delta is yet. So if that is the case, then what should happen is our f of x minus L should be less than epsilon. So just kind of some scratch work there. And what I'm looking at right now, and I know sometimes I want to make sure these are absolute value bars. If I go too fast, that looks like a 4. Take your time. So f of x, and I said 4, and I meant to keep it at an L. Oh, it's getting late. Okay, so we have f of x minus L should be less than epsilon. Okay, so again, you're going to say, who was f of x? We go back and we look at the argument of the limit. And so that should be, in our case, it's 5 minus 4x. And then who is supposed to be the limit? According to our statement that we have, that should be -3. So again, be really careful, because when you're subtracting off the limit, this time the limit is a negative value. So you want to be careful not to skip any steps here. So we have f of x, 5 minus 4x, subtract off -3, that should be less than epsilon. Now what's our goal? If we have this concluding statement, that's our goal, we're going to have to figure out how we can find an absolute value of x minus 2 in there somewhere. When I say find, we have to prove it. We have to algebraically go through the process. So we take that goal, the end statement, and we say, okay, normally it does make sense to see if we can combine like terms and simplify. So if I say 5 minus 4x, subtract off a -3 if you want to take your time on this. I know we're in calculus, we can skip steps, but sometimes it helps just to write everything out. We have 5 minus 4x plus 3. And you know, a lot of times people like to write out. We like to see the x first, maybe. 5 plus 3 gives us 8. Sometimes it's easier on our eyes to write it that way. So now the next idea would just say, okay, well, let's look to see if we can factor out something. We're trying to get an x minus 2 in there. So what I want to write out is, well, it does appear that I can factor out the 4. If I do that, I'll do that in green. Sometimes if there's a negative, we might want to pull that along, but you can kind of play with it to see what works best for what you're looking for. So if one version doesn't work out, try it the other way around. If I pull out a -4 from -4x plus 8, I should get x. And here it is, the x minus 2. Double check yourself too, just in case. So this is what we're looking for. I'm seeing it, but I want to justify how I'm making this an absolute value. So again, one more time, the way these properties are working, if you have a product on the inside, you can rewrite it. So we have the absolute value of -4, which is also multiplied with the absolute value of x minus 2 to give us something less than epsilon. And this is what we need to pay attention to when we're going to go backwards. This is why we do this, this process first. So be real careful. Don't forget this. We're able to say what's the absolute value of -4. That is a 4. Still multiplied by absolute value of x minus 2 is less than epsilon. And so this allows us to isolate the x minus 2. So if you divide by both sides by 4, you're going to get our final delta, epsilon over 4. So once we have delta, we're pretty much home free. We just have to kind of restate everything in terms of the proof. And that step right here with the absolute value of -4, if we didn't work backwards first, we might not be able to figure out what to do in our proof. So look into that. So again, let's start off with the proof. We're going to look at always stating, let's kind of see if I can use the same colors as I did earlier. Always stating what's given. So first off, we are going to write for any epsilon greater than 0. Then the next piece we're going to address, we have a number delta greater than 0. This time we know who delta is. In our case, it's equal to epsilon over 4. So again, I'd like to highlight what I'm doing as I'm going through the proof is I'm stating all the criteria of the hypothesis. The last piece of the hypothesis is for us to speak about if we start off with 0 is less than, in our case, A was 2, x minus 2 is less than, in our case, we let delta equal epsilon over 4. I'll write it in red to remind us. We're going to work our way to see if we can get that final conclusion. And that's where this thought process comes back into play. So if we go through this, again, we're assuming that absolute values are greater than 0, so we can drop off that 0 if this helps. Again, we're looking at absolute value of x minus 2, x minus 2, but epsilon over 4. So if you kind of go back to where we had that last statement, it was at the very bottom. We can now justify why. What we're going to add in right now, or attach in, is that 4. Here we go. Now that's us isolating the epsilon. So 4 times x, absolute value of x minus 2 is less than epsilon. And then here's that piece that we have to remember. We don't want to keep that positive 4. If we try to put that back in the absolute value, we're not going to get our original function back. But the issue was positive 4 is also the same thing as the absolute value of negative 4. We weren't used to that in the previous 2 examples. Okay. So now we're allowed to bring everyone back in. We have absolute value of negative 4 times x minus 2, still less than epsilon, and I'll continue on the proof. And then now we're home free for the most part. Negative 4x plus 8 less than epsilon. And then you may need to relook at your backwards process or your thoughts one more time just to kind of see what we're breaking everyone up into. So if this helps with what we're going with, we can say, okay, that's the same thing. We're breaking that 8 up into a 5 plus 3. I really want to see justification usually. And so now if we kind of look at where our original f of x was, it was supposed to be 5 minus 4x, and we can actually see it right here. Sometimes I take the extra care to really show what I'm looking for. I have 5 minus 4x. I have a plus 3, and maybe that might be useful as well. Instead of a plus 3, we want to remember the limit definition. We are subtracting off a negative 3. So that's kind of where the backward steps do help us out. Is less than epsilon. Let me see if I can move this line over. I want room to write the rest of my proof. There we go. All right. There we go. And finally, if you look carefully, we have just ended with showing what the precise definition of the limit is. So once you have shown f of x minus L is less than epsilon, you can finally conclude your proof with, therefore, the limit as x approaches 2 of 5 minus 4x is equal to negative 3. Then you are concluded with your proof. Are you guys having fun yet? That's a yes, I heard, huh? All right. I had a try at home. Well, everyone's home right now, so we might as well do it together. I'm going to have you prove, and we'll actually do this maybe. It's kind of interesting to see. We've been working a lot with linear functions. So let's see what happens if we have something a little bit different. So let's see if I can give you a little more complication and show you it does apply to everything. So what if we proved the limit as x approaches 2 of x squared plus x minus 6 over x minus 2, prove that that's equal to 5 using, of course, the epsilon delta definition. You might be thinking, whoa, we just went from 0 to 100 in a matter of 2 seconds. We were just dealing with linear functions and now we have a rational function. What are we going to do? But I assure you, you have enough algebra that you've gone over in your past that you could work yourself through this. So let's split up the page into 2 pieces one more time. And we're going to go with our thoughts again. And as far as our thoughts are concerned, remember we're going with the 3-part process. So I can refer back. I wrote it again up here. For any epsilon greater than 0, there's a number delta greater than 0 such that if, so with the thoughts part, we're looking at the if part. So we're going to look at if the distance between x and our given value is less than delta. So let's kind of fill this in for what we see. In our case, our a, okay, so let's say 0 is less than x minus, our a is, x is approaching 2. Okay, so that's what we're going to be looking for. So now, if this is the case, then we should have our conclusion. Remember, the conclusion is f of x minus L is less than epsilon. All right. So if we remind ourselves what the f of x is, it's actually our argument of the limit. So I like to rewrite it, x squared plus x minus 6 all over x minus 2. If I subtract off what the limit's supposed to be, in our case, it's supposed to be a 5. That's supposed to be less than epsilon. So we're trying to prove this in the very end. And usually what happens, if you're kind of going through these, our goal again, if we're going to go through this, our goal is to figure out how to get an x minus 2 somewhere in this particular statement. And this is where we're utilizing everything we learned from intermediate algebra. You have cases of when we were dealing with the linear parts, we're saying a lot of it has to do with maybe combining like terms and factoring stuff out. Sometimes that's the same case, even if we have a more complicated function. You might be interested in kind of looking at it, and you could say, well, I could see if x squared plus x minus 6, that factors, we might have a good time. Other cases of how can we simplify the inside of the absolute value is sometimes you might try to combine over common denominators. See what works. See what you can come up with. And I'll give you kind of a tip here. Remember, our goal is to look for an x minus 2 part, and I'm kind of seeing, I do see an x minus 2 in the denominator, but I can't be clear. I'm not sure if that's what I'm looking quite for. And I like factoring, so I try it. Let's see if we can factor the x squared plus x minus 6. So I just try that first. And if I look at, remember now we're bringing back factoring trinomials to the front of our mind. We're trying to find factors of -6 that add up to 1, we should have an x plus 3 and an x minus 2. So that actually, oh, that's promising. I would be careful before we start trying to cancel everyone out. We kind of have to justify this later. So I want to make sure I'm clear. If I can write this in, technically what we have is we have, this is in mind, we have these x minus 2s, I'll highlight them. Normally we would say, let's get rid of them, but we may need to utilize this somewhere in the proof. So while I'm going to be careful about this, I'm going to see if I can rewrite it so that I have an x minus 2 over x minus 2. That's actually multiplied by the x plus 3. I'll do that still in blue for you. We still have a minus 5 on the outside. And again, we're still less than epsilon all the way through. And let me see if I can play with this. If I were, see if we can go through here, we could bring out some of these. Let's see if we can pull out an x minus 2. Yeah, I'll go with that. All right. This issue right here, I'm going to play with it this way. So kind of keep in mind that this value right here is a 1 no matter what. So we're not quite factoring it outside of everyone, but because it is a number 1, we can pull it out in a sense because 5 times 1 is also 5. So you could rewrite it so that the 5 is multiplied by x minus 2 over x minus 2. I'm not sure how interested you are about this of proving it, but I want to make sure that we're clear. We're not just skipping steps and making up things as we go along. So we wouldn't change the 5 if we were to call it 5 times x minus 2 over x minus 2, because that is still the number 1 right there. And this is the justification of why I'm able to pull this out of the entire absolute value. So let me see if I can rewrite it for you a little bit nicer. I'll keep it in red. So this x minus 2 over x minus 2, technically, if I factor that out of the 2 pieces, I should get an x plus 3 minus 5. And you might think I'm making things more difficult than they have to be, but I'm really wanting to show this later as to why I'm able to work backwards. It does make a difference. So what happens when you are multiplying? You can now pull out the x minus 2 over x minus 2. Let's see that in red. It's multiplied by the absolute value. X plus 3 minus 5 is another x minus 2. That's kind of what we were looking for. But we were clear, yes, it is a 1. So we have the same justification. This was a 1 to begin with. Still multiplied by x minus 2, still less than epsilon, which really implies that your x minus 2 is less than epsilon. Normally we were looking at solving to isolate that absolute value of x minus 2, but at this point we actually found our delta is exactly what epsilon is. So you may have thought that the last few steps that we did, it seems like you don't need to, because we can kind of see right away that if we were looking at x minus 2 over x minus 2, we could have figured it out. But I'm going to have to justify this with logical and sound argument when I do the proof. So I can't just skip the step. So let me go back one last time. We're going to do the proof now. Of our limits. So when we do the proof, one more time, we're always going to start off for any epsilon greater than 0. That is the first part of our definition. The second part of the definition, we define who delta is. So in our case, it was epsilon. And then the third part, kind of where all the algebra comes into play, we're going to have to talk about the if statement. So if we have the case of 0 is less than x minus 2 is less than, this time it's epsilon. That's where it's coming from, and I'll color code that just so you say. Again, sometimes you can leave that step out and go straight to absolute value of x minus 2 is less than epsilon, because we always know distances are greater than 0. Now we're going to justify why we're getting our function back. And this is where you might not have caught it if you weren't able to see this in the particular backwards thoughts. So we're actually at this very last step right now. And if we're trying to figure out what do we have to introduce in order for us to get the function back, there's nothing we can introduce. We do know that we have a number 1 times this. So you can kind of justify it if you need to, that you really have a 1 times the absolute value of x minus 2 is less than epsilon. But most of us are saying, yeah, we know that already. But this 1 has to be in the form of x minus 2 over x minus 2 for our problem to work out. So that's kind of where the extra steps came into play. So instead of writing 1, we can write it as x minus 2 over x minus 2, still multiplied by x minus 2, less than epsilon. And this is where it justifies, well, we don't always have to start off with the x minus 2. We can rewrite this. This 2 part right here, that wasn't like that earlier. It was actually rewritten so that it was x plus 3 minus 5. So there's a couple ways we can go. We could go back to, I'll keep it a little bit nicer for you guys. Just kind of go step by step. X minus 2. And this part right here, still less than epsilon, it was, if we look backwards, x plus 3 minus 5. So we broke up the negative 2 as to a plus 3 and a minus 5, just so that we all can see that. And once we're able to do that, we can talk about where this all came from. You can either show that you are reintroducing the x minus 2's in there. So we go backwards. We keep want to show the, actually I should show a left implication, sorry, pointing to the right. So we're implying, if we were to distribute this back in, what I want to look at is the absolute value of x minus 2. Again, we're working with our backward structure over x minus 2 is actually getting multiplied. I'll try to color code this so that we know the difference between everything. Here we go. And now if we work backwards, we could wave our hands over the previous steps, but what you're trying to show is that you see an x minus 2 over x minus 2 getting multiplied by an x plus 3 with the minus 5 on the outside. So if you would like, you're distributing the x minus 2 to the first part, in a sense, and an x minus 2 over x minus 2 to the second part, just showing exactly what we saw in our past. I'm running out of room. Move that line over because I'm still emphasizing that I have to be less than epsilon. Here we go, less than epsilon. So now you can think about this in two ways. Instead of calling what's next to the 5 as x minus 2 over x minus 2, you can rewrite that as the number 1, just like we did earlier. And if it's the number 1, you don't have to really rewrite it. But you would not get rid of the x minus 2 over x minus 2 by the x plus 3. Reason being is because you're trying to get your original function back. So just kind of pause there and double check. Do you understand why this x minus 2 disappears? Go straight to the 5. If not, it's a good thing to ask the tutor or me if you're not sure. But now we are on our way to getting that original function back. We kind of see, I'd like to separate these a little bit so we have this. We can tell, okay, that's the same thing as x squared plus x minus 6 and it's our steps in reverse. So don't spend too much time multiplying the stuff out if you've already proven it backwards and forwards. Subtracting off of 5 is less than epsilon, and we finally have it. We have limit of f of x minus L is less than epsilon. So let's see if we can finally conclude. We have just shown what we were supposed to show. Final conclusion of the day, we have the limit as x approaches 2 of this function, x squared plus x minus 6 over x minus 2 is equal to 5. Proof concluded. You guys deserve a break. Take one. I'll see you next section.